There is a number that governs almost every living thing on Earth. It predicts how fast a creature's heart beats, how long it will live, how much food it needs each day, and how quickly it burns through energy. The number is 3/4 or 0. 75, and it appears with such stunning regularity across species that biologists once thought it must be some kind of cosmic error in their data. It was not an error. It was one of biology's most profound discoveries, and understanding it changes how you see every animal on the planet. Start with something simple. Why can't insects grow to the size of dogs? It seems like a ridiculous limitation when you actually think about it. Insects have existed for over 400 million years. They have survived mass extinctions, ice ages, and the rise of every dominant vertebrate lineage. They are some of the most successful animals to ever exist, and yet they remain small. The largest beetle alive today, the Titan beetle, reaches about 17 centimeters. The largest spider, the Goliath bird-eater, stretches to about 30 centimeters across. These seem enormous until you place them next to almost any mammal, at which point they shrink to nothing. The reason insects cannot grow larger comes down to physics, and to a piece of geometry called the square-cube law. When you scale any three-dimensional object up uniformly, its volume grows far faster than its surface area. If you double the length of a cube, its surface area increases by a factor of 4, but its volume increases by a factor of 8. This difference compounds rapidly as the object gets larger. It matters enormously for animals because many biological functions depend on surface area. The tracheal system that insects use to breathe is one of them. Insects do not have lungs. They have a branching network of tubes called tracheae that carry oxygen directly to tissues, with air diffusing passively inward from openings on the body surface called spiracles. This system works beautifully at insect sizes because the distances oxygen must travel are short enough for passive diffusion to handle. But as the body grows larger and volume increases faster than surface area, those diffusion distances become too great. The oxygen simply cannot reach the inner tissues quickly enough to sustain a living body. The insect would suffocate from the inside out, not because there was no air, but because the geometry of getting that air where it needed to go had broken down. This is not just theoretical. The fossil record shows this constraint playing out in real time. Around 300 million years ago, during the Carboniferous period, atmospheric oxygen levels climbed to roughly 35%, compared to about 21% today. With more oxygen available to push the diffusion gradients outward, the physical limits of the tracheal system were pushed outward with them, and insects grew to sizes that seem almost fictional by modern standards. Meganeura, a dragonfly-like predator with a wingspan approaching 70 centimeters, patrolled Carboniferous forests. Arthropleura, a millipede-like arthropod, reached 2.5 meters in length and would have been about waist height on an average adult human. These were genuine giants, living proof that the size constraint on insects is not an absolute physical law but depends critically on the chemistry of the atmosphere around them. When oxygen levels eventually dropped, the giants disappeared with them. Vertebrates solved the oxygen problem differently. Lungs are internalized organs, actively ventilated by muscle, with a circulatory system pumping oxygenated blood to every part of the body. This architecture scales in a fundamentally different way, which is why vertebrates can reach sizes that would be flatly impossible for any insect on Earth. But even within vertebrates, scaling imposes its own hard rules, and the most striking of these is Kleiber's law. In 1932, a Swiss biologist named Max Kleiber compiled metabolic data from a range of animals and started looking for patterns. What he found was deeply counterintuitive. Across species ranging from mice to cows, the relationship between body mass and metabolic rate was not linear. It followed a power law, with metabolism scaling as body mass raised to the power of 3/4. A cat weighs roughly 100 times more than a mouse, but it does not burn 100 times more energy. It burns only about 32 times more because 100 raised to the 3/4 power comes out to approximately 32. Large animals are substantially more metabolically efficient per unit of body mass than small ones, and the mathematics is almost eerie in its precision. What makes Kleiber's law genuinely astonishing is how far it extends. The relationship holds across more than 18 orders of magnitude in body size, from bacteria through blue whales, from single-celled organisms to the largest creatures that have ever lived. No other law in all of biology operates across a comparable span. The three-quarter exponent appears so consistently in organisms separated by hundreds of millions of years of evolution and radically different body plans that it cannot possibly be coincidence. It must reflect something fundamental about the physical architecture that makes life work. The most compelling explanation came from physicists Geoffrey West, James Brown, and Brian Enquist in 1997. They argued that metabolic scaling emerges from the geometry of the branching networks that distribute resources inside bodies. Blood vessels in animals, xylem networks in plants, and similar systems in other organisms all share a fractal-like branching structure. Large vessels divide into smaller ones, which divide into smaller ones still, all the way down to the finest capillaries. This architecture maximizes the territory the network can reach while minimizing the volume of space it occupies within the body. When you work through the mathematics of how such a network must behave as body size changes, the three-quarter exponent drops out of the equations as a natural consequence. The law is not arbitrary. It is the mathematical result of efficient resource delivery through fractal branching networks embedded in three-dimensional bodies. The geometry of life itself encodes the number. The cascading consequences of this law reshape almost everything you might assume about how animals live. Because larger animals are more metabolically efficient per unit of mass, they burn fewer calories per kilogram. An elephant consuming perhaps 150 kilograms of vegetation a day fuels its body far more economically than any small mammal. This efficiency cascades into lifespan. The pace of life slows measurably as body size increases. Heart rate drops with rising mass. The Etruscan shrew weighs only about 2 grams and has a resting heart rate of roughly 1/500 beats per minute. It cannot stop eating for more than a few hours without dying, because its metabolic demands deplete its energy reserves almost immediately. A blue whale's heart, the largest organ produced by any animal in Earth's history, can weigh over 600 kilograms and beats perhaps twice a minute. The gulf between those two numbers is almost impossible to hold in your head. Beneath these different rhythms, there is a strange arithmetic. Despite the wildly different rates at which hearts beat across mammal species, most mammals accumulate roughly the same total number of heartbeats in a lifetime, somewhere in the range of 1 billion to 1.5 billion. Small animals live fast and die young. Large animals live slowly and die old. The biology is different, but the accounting comes out remarkably similar. This is not merely a poetic observation. It is a mathematical prediction that falls directly from Kleiber's relationship between mass, metabolic rate, and the subsequent pace of cellular aging. At the physical extremes of size, biology encounters the limits of what is structurally possible. Galileo understood as early as 1638 that scaling an animal up without changing its proportions would eventually cause it to collapse under its own weight. The strength of a bone scales with its cross-sectional area, but the mass it must support scales with volume. An enormous mouse built to the exact same proportions as a small mouse would shatter its own legs the moment it tried to stand. Large animals compensate by evolving proportionally thicker and more robust limbs, but added bone means added mass, which demands still more structural support, pressing steadily against hard limits. The blue whale exceeds the size of any land animal that ever lived precisely because ocean water buoys up its body, removing the engineering constraint that gravity imposes on everything walking on solid ground. The mathematical laws of biological scaling are not failures or limitations that evolution somehow never found a way around. They are the architecture that makes life possible across its entire range. The square cube law explains why the insect giants of the Carboniferous vanished when the oxygen did. Kleiber's three-quarter power law explains why a shrew must eat without pause while an elephant can afford to take its time. The fractal geometry of branching vascular networks explains why both facts are true simultaneously, emerging from a single deep pattern that runs through the structure of living systems. Biology is not simply a collection of remarkable creatures. It is a collection of remarkable creatures shaped and constrained by mathematics. And the numbers, once you know where to look, are written into every single heartbeat.